Hi everyone, welcome back to the channel. In this video, we're going to take a close look at Multicast DNS, or mDNS, and learn how to capture and analyze mDNS traffic using Wireshark on Windows 11. mDNS is widely used by Windows and many modern devices for automatic discovery on local networks, allowing systems to find each other without relying on a traditional DNS server. While this makes networking easier, it also means your computer may be sending and receiving multicast traffic in the background, often without you realizing it. I'll walk you step by step through setting up Wireshark, identifying mDNS packets on the network, and understanding what those packets actually mean. By the end of this video, you'll be able to see exactly how mDNS works on Windows 11, verify when it's active, and confidently analyze this traffic for troubleshooting or security purposes. Before we move on, it's important to understand what mDNS actually is and why it exists, so the rest of the walkthrough makes sense. Multicast DNS, or mDNS, is a protocol that allows devices on the same local network to resolve hostnames without using a traditional DNS server. Instead of sending DNS queries to a central server, mDNS uses multicast communication so devices can discover each other automatically. When a device wants to resolve a hostname using mDNS, it sends a DNS-style query to a multicast address on the local network. For IPv4, this address is 224.0.0.251, and for IPv6, it's FF02FB. All devices that support mDNS listen on UDP port 5353. If a device recognizes the requested name as its own, it replies directly with its IP address. Because mDNS relies on multicast, every device on the local network can see the query. The response may be sent as a multicast or unicast reply, depending on the query flags. This design makes mDNS simple and efficient for small networks, but it also means that devices continuously advertise their presence unless mDNS traffic is restricted. mDNS is most commonly associated with .local hostnames because this domain is reserved specifically for multicast DNS. When a device uses a hostname ending in .local, the operating system knows not to send the request to a traditional DNS server. Instead, it automatically switches to mDNS and broadcasts the query on the local network. The .local suffix acts as a signal to the operating system that the name should be resolved locally rather than globally. This prevents conflicts with Internet DNS and ensures that .local names never leave the local network. Because of this behavior, .local is widely used for device discovery, printers, media devices, and service announcements. On Windows 11, mDNS is enabled by default and integrated into the networking stack. It is used by features such as network discovery, printer discovery, media streaming, and service discovery. Windows listens for incoming mDNS queries and also sends mDNS queries when applications attempt to resolve .local names. From a security perspective, mDNS can leak host names, device names, and services to anyone on the same network. On trusted home networks this is usually fine, but on public or shared networks it may expose unnecessary information. This is why some users choose to monitor, restrict, or block mDNS traffic using tools like Windows Firewall or Wireshark. Now that we understand what mDNS is and how it works, let's move on to capturing and analyzing mDNS traffic on Windows 11. To generate mDNS traffic from one computer and capture it on another, you must first know the exact hostname of the target computer. mDNS uses hostnames ending with .local, so without the correct hostname, the query will not match any device and no meaningful traffic will appear in Wireshark. On the target computer, the one you want to resolve, first click the Start button, type PowerShell in the search box, and press Enter. This will open a PowerShell window. In the PowerShell window, type hostname and press Enter. PowerShell will display the hostname of the computer, which is the unique name used by the system on the local network. Next, you need Wireshark installed on the computer that will capture the network traffic. If Wireshark is not installed yet, go to the official Wireshark website, download the installer, and complete the installation before continuing. Wireshark is required because it allows you to see mDNS packets as they travel across the local network, including both queries and responses. Without it, the mDNS activity would be invisible. After installing Wireshark, click Start, type Wireshark, and press Enter to open it. When the Wireshark window opens, you'll see a list of available network interfaces. Look for the interface that is currently active. This is usually your Ethernet or Wi-Fi adapter, depending on how your computer is connected to the network. You can often tell which one is active by the small graph showing live traffic. Select the active network interface, then click Start Capturing Packets. Wireshark will immediately begin capturing all network traffic on that interface. Now it's time to generate some mDNS traffic. Go to another computer on the same local network. You can use PowerShell to generate an mDNS query from one computer on your local network. This is done using the resolve DNS name command, which asks the network for the IP address or service record of a specific hostname. First, click the Start button, type PowerShell in the search box, and press Enter. This opens the PowerShell window, where you can run commands to query hostnames and services on the local network. In the PowerShell window, type resolve DNS name, followed by the first computer's hostname and .local, then press Enter. This command forces the system to resolve a .local hostname, which automatically triggers an mDNS query instead of normal DNS. Now switch back to the computer running Wireshark. To make things easier to analyze, click on the display filter bar at the top and type mDNS, then press Enter. Immediately, the packet list should narrow down to only mDNS traffic, making it much easier to see what's happening. Now let's slow things down and dig deeper into a single mDNS packet in Wireshark, so you can clearly understand what each column means and why it matters. Let's start by looking at the first packet in the list. The first column is the frame number. This is the packet's position in the capture and shows the exact order in which Wireshark recorded the packets. It does not come from the network itself. It is assigned by Wireshark. The frame number is mainly used to reference a specific packet during analysis. Next, the second column is the time column. It shows the timestamp relative to when the capture started, not the actual clock time. This helps you understand when the packet occurred and how quickly events happen on the network. In mDNS traffic, this is especially useful because queries and their responses usually appear within milliseconds of each other, making it easy to identify request-response behavior and timing patterns. Next, the third column is the source column. This shows the IP address of the computer that sent the packet. By looking at the source column, you can determine which computer initiated the communication, which is especially useful when tracing who is generating mDNS traffic. Next, the fourth column is the destination column. This shows the IP address the packet is being sent to. For mDNS, the destination is typically a multicast address, such as 224.0.0.251 for IPv4 or FF02FB for IPv6. Sending traffic to this address means the packet is delivered to all mDNS-capable devices on the local network, allowing them to receive and respond to the query. Next, the fifth column is the protocol column. This indicates the network protocol Wireshark has identified for the packet. In this case, it shows mDNS, which stands for Multicast DNS. This tells you that the packet is a DNS message sent over multicast, using UDP port 5353, and is part of local name resolution or service discovery on the local network. Next, the sixth column is the length column. This shows the total size of the packet in bytes, as captured on the network. Finally, the last column is the info column. This provides a human-readable summary of the packet's contents, decoded by Wireshark. In detail, it contains the following elements. First, the info column contains the message type, such as standard query or standard query response. This part tells you the role of the packet in the mDNS exchange. A standard query means the packet is asking a question. The sender is requesting information, such as an IP address or service record, and does not contain any answers. In mDNS, a standard query is typically sent to the multicast address so that any computer on the local network that can answer may respond. A standard query response means the packet is replying to a previous query. This type of packet contains one or more answer records that provide the requested information, such as the IP address associated with a hostname or details about a service. In mDNS, responses are usually sent via multicast. However, in certain situations, responses may be sent via unicast directly to the requester, which helps reduce network traffic. Next, the info column contains the DNS transaction ID. This is a 16-bit value in the DNS header that identifies a specific query. In standard unicast DNS, the transaction ID is crucial. The client assigns a unique ID to each query, and the DNS server copies that same ID into the response. This allows the client to match each response with the correct query, especially when multiple DNS requests are in progress at the same time. In mDNS, the transaction ID works differently. Because mDNS uses multicast, multiple devices may respond to the same query, and responses are not matched using the transaction ID. As a result, the transaction ID in mDNS packets is typically set to 0x0000. Next, the info column contains the record type. This indicates the kind of DNS data the packet is asking for in a query or carrying in a response. By looking at the record type, you can immediately understand the purpose of the packet, such as whether it is asking for an IP address, advertising a service, or supplying additional service details. One of the most common record types is the A record, which is used to map a hostname to an IPv4 address. When an mDNS packet contains an A record, it indicates that the packet is either requesting or supplying the IPv4 address for a specific hostname. This record type is typically used when a device needs to resolve a .local hostname to an IPv4 address on the local network. Similarly, another very common record type is the Quad A record, which serves the same purpose but for IPv6. When an mDNS packet contains an Quad A record, it indicates that the packet is requesting or providing the IPv6 address associated with a hostname, allowing devices to resolve .local names in IPv6-enabled networks. For service discovery, mDNS relies heavily on PTR, SRV, and TXT records. A PTR record is the entry point for service discovery. It answers the question, what services of this type are available on the local network? Instead of pointing a hostname to an address, a PTR record maps a service type to a specific service instance name. This allows clients to discover that a particular service exists and learn its advertised name. An SRV record then provides the connection details for that service instance. It tells the client which hostname is running the service and which port number to connect to. Without the SRV record, the client would know a service exists but would not know where or how to reach it. A TXT record supplies additional descriptive information about the service. This can include configuration options, supported features, versions, or other metadata expressed as key-value pairs. TXT records help the client understand how to interact with the service correctly, beyond just knowing its address and port. Together, PTR, SRV, and TXT records allow mDNS to fully describe a service. PTR discovers it, SRV locates it, and TXT explains it. Next, the info column contains the queried name or service. This shows exactly what the packet is asking about. For regular name resolution, the queried name is usually a host name. This indicates that the sender is trying to resolve that local name to an IP address. For service discovery, the queried name is often a service type or a specific service instance. This tells you whether the packet is searching for all services of a certain type or referring to a particular service on the network. By looking at the queried name or service in the info column, you can quickly understand what the sender is requesting. Finally, the info column contains the query mode, which indicates how the query expects a response. In mDNS, this is usually shown as QM, Query Multicast, or QU, Query Unicast. QM means the query is sent to the multicast group, so any device on the local network that owns the requested name or service can respond publicly. QU, on the other hand, means the query expects a direct unicast reply back to the sender only. The query mode is important because it shows whether responses are broadcast to all devices on the LAN or sent privately to the requester. Most mDNS queries use QM, since mDNS is designed for open service discovery and local name resolution. In summary, the info column allows you to quickly understand the purpose and behavior of the packet without having to open the full protocol details in Wireshark. Now, let's take a closer look and walk through each mDNS packet in Wireshark, step by step, so you can understand what each one does. Packet 56 is an mDNS standard query sent by the computer with IPv4 address 192.168.100.166 to the IPv4 multicast address 224.0.0.251. The mDNS query includes the name field set to desktop, E770LG0.local, specifying the hostname being resolved, the type field set to A, indicating a request for an IPv4 address record, and the QU flag is set to false. meaning the query expects a multicast response delivered to all computers on the local network rather than a unicast response sent directly to the requesting computer. In other words, the computer sending this packet is asking, who has the hostname desktop E770LG0.local, and what is its IPv4 address? Next, packet 57 is an mDNS standard query sent by the computer with IPv6 link local address FE80, D55F, 5552:9B60:3856 to the IPv6 multicast address FF02FB. The mDNS query includes the name field set to desktop E770LG0.local, specifying the hostname being resolved, the type field set to A, indicating a request for an IPv4 address record, and the QU flag is set to false, meaning the query expects a multicast response delivered to all computers on the local network rather than a unicast response sent directly to the requesting computer. In other words, the computer sending this packet is asking, who has the hostname desktop E770LG0.local, and what is its IPv4 address? Next, packet 58 is an mDNS standard query sent by the computer with IPv4 address 192.168.100.166 to the IPv4 multicast address 224.0.0.251. The mDNS query includes the name field set to desktop E770LG0.local, specifying the hostname being resolved, the type field set to quad A, indicating a request for an IPv6 address record, and the QU flag set to true, meaning the query requests that responses be sent as a unicast reply directly to the requesting computer rather than as a multicast response to all computers on the local network. In other words, the computer sending this packet is asking, who has the hostname desktop E770LG0.local, and what is its IPv6 address? Next, packet 59 is an mDNS standard query sent by the computer with IPv6 link local address FE80, D55F, 5552:9B60:3856 to the IPv6 multicast address FF02FB. The mDNS query includes the name field set to desktop E770LG0.local, specifying the hostname being resolved, the type field set to quad A, indicating a request for an IPv6 address record, and the QU flag set to true, meaning the query requests that responses be sent as a unicast reply directly to the requesting computer rather than as a multicast response to all computers on the local network. In other words, the computer sending this packet is asking, who has the hostname desktop E770LG0.local, and what is its IPv6 address? Next, packet 60 is an mDNS standard query response sent by the computer with IPv4 address 192.168.100.165 to the IPv4 multicast address 224.0.0.251. The mDNS response includes the name field set to desktop E770LG0.local, specifying the hostname being answered, the type field set to A, indicating an IPv4 address record, and the address field containing 192.168.100.165, which is the IPv4 address associated with that hostname. In other words, the computer sending this packet is answering the question, the hostname desktop E770LG0.local is associated with the IPv4 address 192.168.100.165. Next, packet 61 is an mDNS standard query response sent by the computer with IPv6 link local address FE80, 8042:18BD, 1894, AF9 to the IPv6 multicast address FF02FB. The mDNS response includes the name field set to desktop E770LG0.local, specifying the hostname being answered, the type field set to A, indicating an IPv4 address record, and the address field containing 192.168.100.165, which is the IPv4 address associated with that hostname. In other words, the computer sending this packet is answering, the hostname desktop E770LG0.local is associated with the IPv4 address 192.168.100.165. Next, packet 62 is an ICMP packet, not an mDNS packet. This ICMP packet indicates that a router at IPv4 address 192.168.100.1 dropped a packet after TTL processing and notified the original sender at 192.168.100.165. The ICMP message appears alongside mDNS traffic because the system misroutes link local multicast packets toward the default gateway instead of keeping them on the local link. Since mDNS uses link local multicast and must not be forwarded by routers, the router discards the packet and generates an ICMP, time to live exceeded, response to the sender. You can ignore this ICMP, time to live exceeded, packet. It is a control message generated by the router in response to unrelated routing behavior. Wireshark shows ICMP TTL exceeded packets under the mDNS filter because the ICMP message contains the original mDNS packet header. Next, packet 63 is an mDNS standard query response sent by the computer with IPv6 link local address FA80/8042:18BD 1894 AF9 to the IPv6 link local address FA80/D55F 5552:9B60:3856. The mDNS response includes the name field set to desktop, E770LG0.local, specifying the hostname being answered, the type field set to quad A, indicating an IPv6 address record, and the address field containing FA80/8042:18BD 1894 AF9, which is the IPv6 address associated with that hostname. In other words, the computer sending this packet is answering, the hostname desktop, E770LG0.local is associated with the IPv6 address FA80/8042:18BD 1894 AF9. Next, packet 64 is an mDNS standard query response sent by the computer with IPv4 address 192.168.100.165 to the computer with IPv4 address 192.168.100.166. The mDNS response includes the name field set to desktop, E770LG0.local, specifying the hostname being answered, the type field set to quad A, indicating an IPv6 address record, and the address field containing FA80/8042:18BD 1894 AF9, which is the IPv6 address associated with that hostname. In other words, the computer sending this packet is answering, the hostname desktop, E770LG0.local is associated with the IPv6 address FA80/8042:18BD 1894 AF9. And that brings us to the end of how to capture and analyze mDNS traffic using Wireshark on Windows 11. At this point, you should be able to recognize mDNS traffic, understand why it uses multicast, and read each Wireshark column to quickly identify who is asking, who is responding, and what information is being exchanged. You've seen how mDNS queries and responses work, how to identify hostnames, record types, and response modes, and how to interpret what each packet is doing on the network. If you found this helpful, don't forget to like the video, and subscribe to the channel. Thanks for watching, and I'll see you in the next one.